So have a look at page 37. Okay, so let's have a look at the notes. There's one part I need to cover with you before we can even do this question. All right, so if you just look at page 12 of your notes first, okay, have a look at page 12 of your notes. I need to go through this part with you before we can do page 37. Now, we already know that simple harmonic motion always follows this equation. A equals to negative omega square x. This one, as I mentioned to you quite a number of times, this is the defining equation of SHM. Okay, anything that follows SHM must follow this equation. All right. But the thing is that when you look at some of your questions and they tell you that the object is undergoing simple harmonic motion, the equation that they give you to describe its motion can be another different equation instead. Okay, motion of a system undergoing simple harmonic motion can sometimes be described by another different equation. But at the same time, you know that because it's simple harmonic motion, it must obey the defining equation of SHM in the first place. So what you will want to do after that, if you want to solve the question, is that you will try to compare that given equation to the defining equation of SHM. You try to compare them and see the similarities between them. It's a bit the same as what you guys have been doing in paper 3, question 1. If let's say I give you some equation f is equals to kx, and I ask you to plot graph of f versus x and find the value of your k, you would probably say to me, yeah, you compare this to the equation of a straight line. You will say that the y-axis should have been representing your force, the x-axis should have been representing your extension, and then after that, your constant, spin constant, is actually represented by your gradient. So this is what you have been doing in paper 3, question 1 regularly, isn't it? You are given some sort of equation which you do not understand, but then you are asked to find the value of a constant. And what you did was that you tended to equate it to the equation of a straight line, and then you find whatever you need from the gradient as well as the y-intercept, isn't it? So something similar is happening here right now. You are given some equation that you don't know, but then you want to find something out of it. What you do is that you compare the equation with the defining equation of SHM, much like you do when comparing to straight line equation. From there, you work out something from that. Okay, so an example of that will be given below here. If you have a pendulum bob, and I tell you that the oscillation of the pendulum bob is described by this equation, AL is equals to negative GX. I want to find out certain things like, say, the frequency of oscillation. How do I go about doing this? What you do is that you want to compare it to simple harmonic equation, a simple harmonic motion equation, A equals to negative omega square x. You change your given equation such that the form matches this one. So if I try to change this given equation such that its form matches the defining equation, it will actually look like this now. A is negative GL over A is equals to negative GL x. Okay. So if you go and change it about, you're going to get something like this now, where you say A is negative G over L times X, then A is negative omega square X. You can see that this and this is already matching each other, but your omega square, negative omega square, is actually equal to negative GL. That's why here I can say that omega square is equal to GL. Now from here, you can actually then work out a few things like finding out your frequency or finding out your period by just subbing in omega as 2 pi f, and then after that find f, and subsequently saying that f is actually 1 over t. Okay, so this is what I meant by you comparing your given equation with the defining equation of SHM and then finding something out of it. It can be your frequency, it can be your angular frequency, it can be your period. Okay, it depends on the context of the question. Now, if you look at the second example here, it's a similar thing. If let's say you have a mass spring system and they tell you that your mass spring system, the motion can be described by this equation, ma equals to negative kx, you want to compare with the defining equation of SHM. So you purposely change its form to match that of the simple, to match that with the defining equation. So ma equals to negative kx will be similar to a equals to negative kmx. So from here, if you say a is negative k over mx, you compare with a equals to negative omega square x, you can now say that a is a here. Then after that, omega square is k over m, and x is still x. So here, omega square is equals to k over m. From here, you can work out your omega, you can work out your f, you can work out your t. Okay, so this is how you will proceed if given some other equation, but we tell you at the same time it is simple harmonic motion. All right, so far so good. All right, so that one is okay. Then I move on to your question again. Now have a look at page 37. Okay, have a look at page 37 of your worksheet. Now, in your current question, they tell you that a U-tube contains liquid as shown in figure 4.1. The total length of the liquid column is L. The column of liquid is displayed so that the change in height of the liquid level from equilibrium position in each arm of the U-tube is x, as shown in the figure. The liquid in the U-tube then oscillates such that its acceleration A is given by this expression, where G is the acceleration of free fall. Now show that the liquid column undergoes simple harmonic motion. Okay. You have a U-tube that looks like this right now. You displace it towards the side. The liquid inside the U-tube will start to oscillate up and down. So it oscillates up and down. One part will move up, one part will move down from some sort of equilibrium position. And they mentioned to you that your displacement is measured as x here from equilibrium. Okay, so the equation to represent the oscillation of the U-tube is this one. Now, your question here isn't really asking you to calculate something out of it, but rather they're just asking you to show that the liquid column undergoes simple harmonic motion. So this one, it's not really related to what I just mentioned to you yet because it doesn't involve calculation. This one is just really asking you to show that from this given equation, it is undergoing SHM. So what you can do is something like this. Wait, let me open up the question, November 2018, P42. How would you show that from that given equation, your object is undergoing SHM? Now, if in general, I told you that A is equals to negative omega square x, from an equation, you can actually also prove that something is following SHM. Okay, the previous question before this, I mentioned to you that you can prove that something is following SHM by looking at the graph shape. Straight line to origin is acceleration directly proportional to displacement. Negative gradient shows that your acceleration and displacement are always in opposite direction. That one was what we did in the previous question. Now, when it comes to proving something is simple harmonic motion, you can actually also prove it from equation. Say I give you a simple equation like this. How do I see this and say that it is following simple harmonic motion? You can say something like this. If omega square is constant, therefore, if omega square is constant, therefore A is directly proportional to X. And then negative means A and X are in opposite directions. This is by equation, proving SHM by equation. The previous example that I just did with you, that one is proving something is SHM by diagram, by a graph. So similarly, you can also prove that something is SHM by equation. The general answers will be something like this, no? You have to say that something is constant first, like this one is constant. Only then can you say A is directly proportional to X. And then after that, you single out the negative sign. Negative sign means to you that A and X are in opposite direction. Back to this question here, you have a given equation here. Show that the liquid column undergoes simple harmonic motion. So for this one, you can actually just kind of look at it as this. Just don't bother about what I wrote here, right? Because I think it's more complicated than necessary. A is negative 2g over L times X. So the first thing you say is this: G and L are constant, therefore A is directly proportional to X. And then after that, you just say the negative sign means that A and X are in opposite directions. So based on these two, you can just say therefore SHM. Okay. These are the two things that you really just need to write in order to prove that your object is undergoing SHM. What I've written on the work solutions here is actually kind of same, but I don't think it's as straightforward as that, as what I just written on the screen here. Here I say defining equation of SHM is A equals to negative omega square X. There's actually no relation to write this. Then I say A is equals to negative 2g over Lx. G and L are constant, therefore A is proportional to negative X. Then A is proportional to X. A and X are always in opposite direction, therefore it's SHM. It's talking about the same thing, but I think the ones that I just wrote here is actually much more straightforward. Okay. Right. So this is for this page. If you're okay with that, then I'll move on to the next one. Okay, so move on to the next one. This is where you need to talk about comparing your given equation with your SHM, defining equation of SHM. So let me clear this one off. Now the variation with time t of the displacement x is as shown in the figure below. Use the data from the figure to determine the length L of the liquid column. Okay, use the data there to determine length L of the liquid column. So this is a proper displacement from equilibrium versus time graph. All right, no tricks here. Now you want to determine length L of the liquid column. It was mentioned to you that A is negative 2g over L times X. Now, if you compare with the defining equation of SHM, A is equals to negative omega square X, you can come to the conclusion that omega square is equals to 2g over L. It's actually saying this. Okay. Now, you want to find L, but you are missing some other stuff in order to be able to find L. Specifically, you do not know what is omega. So if only you know omega, you can actually work out what is L. Now, coincidentally, you also know that omega is 2 pi over t. Your graph here actually allows you to find out what is t, where t is right over here, where t is actually 0.5 seconds. So after you say that omega squared is 2g over L, you go and say that it is 2 pi over t squared equals to 2g over L. Then you sum in the value of t and all relevant values. Eventually, you get the answer for L at 0.124 meter. Okay, so this one is the answer for this one. Okay, so just plug in the values and you get the answer 0.124 meter. Pretty straightforward. Okay, is something similar to what you've done in paper 3 question 1 before. You need to kind of compare with equation of straight line, but here you just compare with defining equation of SHM. Okay, so if this one is okay, then I move on to the last two parts of your question. All right, before I give you a break. Now, if you move on to the next part, they tell you the oscillation shows in figure 4.3 are damped. So just one cause for this damping. All right. Now, damping I actually haven't really gone through with you. It's actually at the beginning part of your chapter. For your case here, I can just mention to you that when oscillations are damped, the amplitude decreases with time due to energy loss. Okay. A damped oscillation looks like this. Sorry, maybe I should just draw it properly for you. If you have something like this, this one is undamped oscillation. Okay, amplitude is constant. When you have damped oscillations, this same graph would probably look like this. Okay, notice what's happening to the amplitude. This is what we call damped oscillation. Okay, where amplitude decreases with time. Okay, now the cause of the amplitude decrease is because your oscillation is actually losing energy. All right, so one of the reasons why your oscillation could be losing energy, in your case, the question is asking you the reason for the damping, is because there is friction between the walls of your tube and your liquid. So the friction actually causes energy loss. That's why your oscillation would have amplitude decreasing with time. Okay, so you look at your diagram, you have a tube and then you have a liquid inside. Okay, you have the tube here and it's inside a you have a liquid and it's inside a U-tube. Okay, so as the liquid oscillates up and down, as the liquid flows up and down inside the tube, it's actually rubbing against the tube. So there's friction here. So that friction is the one that causes you to have energy loss. Because you can kind of think of it as this way. When the liquid is trying to move, it's doing work against friction. So the friction is causing energy loss. But here you don't really need to explain that much. You just say that there's friction between the walls of the tube and liquid. It causes energy loss. Therefore, there's damping. All right. So that one is for this question. Now, for the last part, calculate the ratio of total energy of oscillations after one complete oscillations to total initial energy of oscillations. Okay. Find out the total energy after 1.5 oscillations compared with the initial energy of oscillation. Okay. So to do this one, you see they mentioned total initial energy, right? Sorry, total energy here. You already learned that when it comes to total energy, is half m omega squared x naught squared. You really need to use your amplitude values here. So let's have a look at your graph again. If I look at the graph, the initial energy of oscillations would be here. This is my initial energy. Then they say after 1.5 oscillations, right? So this one is 1. And then this one is another half. This is 1.5 oscillations later. So this is your final energy. Okay. They want you to take the ratio of your final energy after 1.5 oscillations to your initial energy. Okay. So it helps that your graph here is actually your displacement versus time graph, which in your case, your displacement is really measured from equilibrium. So here you can actually just really just take the value of your amplitude straight from the graph without having to minus anything, unlike before. Okay, you can actually just straight away take the values of your amplitude from the graph here. Okay, so your energies is between these 2 points. You read your amplitude at these 2 points, relate it to your equation here, and then find your ratio. Okay, so how do you get the final answer eventually? You just look at it like this, no? All right, you just look at it as this. Et is half m omega square x naught square. The mass and the omega are constant. Therefore, Et is proportional to amplitude square. So the ratio of the energies will be the ratios of the amplitude squares. So in your case, it will be 1.3 square divided by 2 square, giving you 0.423. Okay. Now you may be wondering, how do I know that omega is constant? Mass constant, this one can be easily understood. How do I know omega was constant in the first place? Because I know omega is 2 pi over t. T is constant. Omega is constant. If you look at your graph, you only see that the amplitude is decreasing. But for all manners and purposes, the period actually had remained the same. So if period is the same, omega would be the same. That's why I can say omega here is constant. Okay. And another thing to note here is this. Your units don't need to change to meter from centimeter because the units actually will cancel each other off since it's a ratio. Okay. So what I mean by that is this. If you have centimeter square here and then centimeter square here, it will just cancel each other off. Even if you change to meter, 10 power minus 4 meter square, 10 power minus 4 meter square, it will still cancel each other off. So make your life simpler, don't need to bother about the units because they cancel off. All right? So your final answer is 0.423. Okay, so have a look at page 19 of your worksheet. So if we look at page 19, it's this one, March 2017 P42. Okay, so for March 2017 P42, we have this question here. Now notice this diagram is similar to the question that we did earlier just now, where they had a very strange looking graph that looks like an acceleration versus displacement graph, but it's actually not the one that we want. So you have a uniform beam that is clamped at one end. A metal block of mass m is fixed to the other end of the beam, causing it to bend as shown here. The block is given a small vertical displacement and then released so that it oscillates with simple harmonic motion. The acceleration A of the block is given by this expression. A is negative k over m times x, where k is a constant for the beam, and x is the vertical displacement of the block from its equilibrium position. Now explain how it can be deduced from the expression that the block moves with simple harmonic motion. So here they're asking you to explain from your given equation, how do you know it's simple harmonic motion? Now in the first place, you can say that k is a constant in the first place because they already told you it's a constant here. And then m is also a constant. M here is referring to the mass of the block. As the object is oscillating, the mass is not going to change, so it's constant. So the ratio of K and M is actually, the ratio of K over M is actually a constant, all right? K over M is a constant, therefore acceleration is directly proportional to displacement, all right? You must write what is constant first before you can say A is directly proportional to X, okay? So this statement is very important to have before you can say A is directly proportional to X, okay? Then the next thing you can probably talk about is the fact that you have a negative sign here. The negative sign shows that acceleration and displacement are always in opposite directions, okay? So therefore, your motion is going to be simple harmonic motion, okay? It's these 2 points that you will always be using a lot. Now for the beam, K is 4 kg per second square. Show that the angular frequency omega of the oscillation is given by this expression here. So this one, you need to compare your given equation with the defining equation of SHM. First is A equals to negative K over mx. Second is A equals to negative omega square x. You compare both of them, you should be able to see quite easily that K over m is actually omega square. Okay, so giving you this. Then after that, omega is square root K over m. And since the value of K has already been given for you, sub it in and then simplify your expression, you're going to get 2 over square root m as omega. Okay, so this one is shown. Pretty straightforward. Okay, then this one is done. Then after that, we go to the next one. They mentioned that the initial amplitude of the oscillation of the block is 3 centimeter. Use the expression in B to determine the maximum kinetic energy of the oscillations. Here you see they actually specifically ask you to use expression in B. Okay, the expression in B was omega equals to 2 over square root m. Okay, we will eventually need to use this. All right. Now they want you to find maximum kinetic energy of oscillations. So Ke max from the last lesson we know is half m omega square x naught square, which is also E total. Okay. But here we relate it to being maximum Ke. So here, what can I say? Ke max, here I wrote it as Ek max now. Okay. There's no need for you to show the derivation like this. You can just straight away say Ke max is half m omega square x naught square. So now if you see that this is the equation for Ke max, you know that the amplitude is 3 centimeter. So that will cover this. But you do not know what is the mass. You also do not know what is the omega. So you actually can't proceed. So there's a way to go about this. Remember that they asked you to use the expression in B. So if you remember the expression in B, omega is equal to 2 over square root m. Omega square in turn is actually 4 over m. So what you want to do is that you want to sub out for omega square. You notice that if you sub out for omega square, you're going to get Ek max is half m times K over m times x naught square. So here, it becomes readily apparent that you can cancel off the mass, giving you half k x naught square. Now you know what is k, it is 4 from the previous page. You know what is the amplitude, it is 3 centimeter, change to meter here. Square the amplitude, you're going to get Ek max as 1.8 times 10 power minus 3 joules. Okay, so this one is for this question. Now for part D, over a certain interval of time, the maximum Ke of the oscillations in C, which is the one here, has been reduced by 50%. It may be assumed that there is negligible change in the angular frequency of the oscillations. So this statement alone already kind of told you that omega is constant. Okay. Now, after your object has lost 50% of its kinetic energy, find out the new amplitude of this oscillation. There's actually two different workings that you can do here. Either you use the normal ratio method of doing things, or either you do something a bit more straightforward. But let me just kind of briefly describe the longer method here first. We know that Ke max is half m omega square x naught square. In your case, the mass remains constant and omega is constant here as stated here. So Ke max is actually proportional to your amplitude square. So the new Ke max to the old Ke max is the new amplitude square to the old amplitude square. Because your new Ke is reduced by half, that means your Ek max 2 will be 0.5 of Ek max 1. That's why here I can say the ratio is just 0.5 to 1. Okay. Then after that, your amplitude values, the initial amplitude was 0.03 meter. The one that you want to find is the new amplitude, which is this one. So you solve everything, you're going to get the answer as 2.12 times 10 power minus 2 meter. This is the new amplitude. Okay. So if you've been using ratio methods to do your questions, this one would look quite familiar to you, but there's actually a far easier way of doing this. That one is actually the one that's written in red here. So remember just how I told you Ke max 2 is 0.5 of Ke max 1. Now Ke max 2, you can just straight away just say this as half K x naught square equals to 0.5 times 1.8 times 10 power minus 3. You see your Ke max 1 is actually this value right over here, which you already found in the previous question. And then your Ke max 2, your expression, how come I write it as half K x naught square? It's because I took it from here. I know that originally it might be half m omega square x naught square, but I know that if I substitute in for omega square, my Ke max expression is actually just half K x naught square. Okay, so from here, if I just bother to sub in the value of K as equals to 4, my x naught would just be 2.12 times 10 power minus 2 meter. No? I'll be getting the same answer as before. Okay, so this one is actually kind of easier to understand and is very straightforward. All right, so this one is for this question. Let me see whether do you guys have the damping question inside. All right, this one part A, I think I'll skip it first because it relates to EM induction. I haven't formally covered EM induction for you guys, so I won't go through that one yet. Okay, so that one is page 19. Next question that we can go through is page 15. So have a look at page 15. Okay, this one is page 15, right? So page 15 is November 16 P41. Let me just have a look at the other question here. November 16 P41 would be this one. Okay. Now to demonstrate simple harmonic motion, a student attaches a trolley to two similar stretch springs. The trolley has a mass of m of 810 grams. The trolley is displaced along the line of the two springs and then released. The subsequent acceleration A of the trolley is given by this expression here. A is equals to negative 2kx over m, where the spring constant k for each of the springs is 64 Newton per meter and x is the displacement of the trolley. Show that the frequency of oscillation of the trolley is 2 Hertz. Okay, so if you're given an equation to describe the motion of the oscillation, almost always you have to compare it with the defining equation of SHM. So here A is negative 2k over m times x, compare with the defining equation of SHM, you will see that 2k over m is actually equals to omega squared, which is this one. And then omega is 2 pi f. So don't forget to square it, equate it to 2k over m, and substitute in all the required values. You already know that k is 64 Newton per meter. You also know that the mass is 810 grams. Don't forget to change it to kg. So sum in everything and do your maths properly, you should get the answer as 2 Hertz as shown here. Okay, so this is for the first part. Pretty straightforward for 3 marks question. Okay. Then if you look at part B, this one off. Now if you look at part B, they now mention to you that the maximum displacement of the trolley is 1.6 centimeter. Calculate the maximum speed of the trolley. So from doing all those questions so far, you should know that Vmax is omega x naught. Okay, you do not know omega straight away, but you can say that omega is 2 pi f. You can make use of what you found here. They told you frequency is 2 Hertz, right? So omega, you make use of 2 pi f, multiply with x naught, sub in all your required values, you will get the answer finally as 0.201 meter per second. Okay, so this one is another pretty straightforward question, which is worth 2 marks. So if this one is okay, then we will move on to part C. Now part C is more on something like state and explain, which you again can use common sense or which you can kind of deduce from the equations. Now, the mass of trolley is now increased. The initial displacement of the trolley remains unchanged. Suggest the change, if any, that will occur in the frequency and maximum speed of oscillations of the trolley. If your mass has been increased, what will actually happen to your frequency? What will actually happen to your maximum speed? Now, if you use common sense a little, you probably might have guessed that, yeah, because your mass has increased, it probably should oscillate slower. So if it's oscillating slower, your period should be increasing. So therefore, your frequency should be dropping. So frequency decreases. And because it's oscillating slower, your maximum speed is also lower. So it's lower, T increase, frequency drop. So your max speed also drop. Okay, this one is like common sense. I mean, most people, when you think about it, because it's having a larger mass, it obviously would be moving slower, your period will be larger, your frequency will be smaller then, and then your maximum speed will also be smaller. Okay, but you really want to prove it from an equation, you can do so if you wanted to, which is actually a better way of going about this kind of question. Now, frequency, we know that from the previous question, omega squared is 2k over m. Omega is 2 pi f square. Sorry, omega is 2 pi f. So sub it in, we get 2 pi f square equals to 2k over m. So if our case now, 2 pi and k is constant, that means f square is inversely proportional to mass. From here, we can easily see that if the mass increases, your frequency drops. So that will actually kind of explain this part. Now, when it comes to the maximum speed part, we know that just now Vmax is omega x naught, or rather 2 pi f x naught. Now, if your x naught remains constant, that means Vmax is proportional to f. If your f decreases, your Vmax would therefore drop. So this will explain this one. Okay, so that is for this. Right, now, your x naught remains constant here is more due to the fact that they mentioned this. They told you the initial displacement of your trolley remains unchanged. Okay. Now you see, the thing that I probably should mention to you now is this. Let's just say, for example, I give you a mass on the string, a pendulum bob. Say this one is your pendulum bob example. If I told you that I initially gave it an initial displacement of say 3 centimeter, and then I release the pendulum bob, I know that the pendulum bob will just start to move like this, like this, like this, and then like this, on and on and on, right? So the thing now is this. As the bob oscillates, its amplitude will never be larger than the initial displacement. Okay, this is because of conservation of energy. Because of conservation of energy. Okay, so if my displacement initially was 3 centimeter, I release the pendulum bob, the bob will just oscillate with a maximum amplitude of 3 centimeter. It will never ever exceed that value because of conservation of energy. All right. If let's just say your pendulum bob suddenly has an amplitude more than the initial displacement, in your case, say maybe it's 5 centimeter, this would have meant that your pendulum bob somehow gain energy during its oscillation, which should not be the case here. When you initially displace your pendulum bob and then release it, there should be no other energy input to your oscillations. So by right, as the pendulum bob oscillates, its amplitude will never ever exceed 3 centimeters here in your current case. Okay. It can drop because of energy loss, but it will never be more than your initial displacement. Okay. That's the thing that I just kind of want to mention here. All right. So here they mentioned this part here where the initial displacement of the trolley remains unchanged. The initial displacement of the trolley remains unchanged actually kind of implies to you that the amplitude remains the same as before. The maximum amplitude of oscillation. Sorry, let me just write this properly. Maximum amplitude of oscillation remains the same. Okay, so that's why here I can then relate it to saying that amplitude actually remains the same. Okay, it will only be able to drop, but it will never be able to gain. I mean, your amplitude of your oscillation, it will never be more than what your initial displacement is, but it can actually drop because of energy losses. All right, that's the reason now why I go and purposely put in the term maximum amplitude here. Okay, because you should know that when something is oscillating, if it's oscillating like this, these are also known as your amplitude, right? Okay, same goes with these points here. All these are known as your amplitude, but this point particularly will be known as your maximum amplitude. So this one can never exceed initial displacement. Okay, that's what I've been trying to tell you right now. Okay, so if this one is okay, then we move on to the next question. Next question would be page 27, if I'm not mistaken. Okay, so Let me just kind of move to another question. Okay, page 37, is it? Wait on. Page 27, sorry. Okay, now move on to page 27. Let's just move on to page 27. Okay, now for your case here, this is November 17 P42. Let's have a look at that. Entry. Now, define the radian. Radian is actually something that you've learned from circular motion. This one, you would say that is the angle subtended at the center of a circle where the arc length is equal to the radius. This is actually talking to you about unit of angular displacement. Unit of angular displacement, where you say that S is r theta, so theta is S over r. If this one is 1, arc length must be 1, radius must be 1. Ratio must be 1 to 1 now. That's why here we say arc length is equals to the radius. All right. Now, second part. State what is meant by angular frequency. This one we just did one in one of the questions just now. We can just simply say that angular frequency is frequency expressed in terms of radians per second, or written in equation form is just this. Okay, so this one not a big issue. Then part B, a thin metal strip clamped horizontally at one end has a load of M attached to its free end as shown here. The metal strip bends. When the free end of the strip is displaced vertically and then released, the mass oscillates in the vertical plane. Theory predicts that the variation of the acceleration A of the oscillating load with displacement x from the equilibrium is given by this, where L is the effective length of the metal strip and A is a positive constant. Now explain how the expression shows that the load is undergoing simple harmonic motion. So again, given equation here, prove that it's following simple harmonic motion. Your question has 2 marks, so there are 2 points that you need to write. So here, looking at it, you can see that this one, C over ml cubed, should be a constant, so that you can say acceleration is directly proportional to displacement. But how do I know that C over ml is going to be constant in the first place? You look at the definition of these variables properly. C is a constant. L is the length of the metal strip, which is also a constant. And then big M is actually your mass, which should by right be constant also. So you can just say that everything here, C over ml cubed, is constant. And then from there, you say that the minus sign shows that acceleration and displacement are in opposite directions. Therefore, therefore the motion is simple harmonic. Okay. Now the last statement here, when you specifically say therefore the load is undergoing simple harmonic motion, is actually not necessary to be written. It doesn't bear any mark, but I just wrote it there for the sake of completeness. Okay, so this one is okay. Then I'll just clear off the diagram here. All right. Now for the metal strip of length 65 centimeter and a load of M 240 grams, the frequency of oscillations is 3.2 Hertz. Calculate the constant C. So here you have a given equation and you need to calculate something out of it. One way to go about it, as I mentioned, is compare the equation with the defining equation of SHM. From here, you'll be able to see very clearly that C over ml cubed is actually equals to omega squared. Okay, so since the one L, you need to know all the other values. Okay, sorry, not the value L. Since they want the value of C, you need to know all the other values. Okay, so mass, you know, length, you know, omega, you don't know directly, but you do know the frequency because it's written here. So omega, you express it as 2 pi f square equals to C over ml cubed. So sub in your values. your final value of C would be 26.6 kg meter cube per second square. Right? So this one is for this one. Pretty straightforward. Okay, so this one is done. And let me see the other questions again. You have 33, 35, and 37. These are the remaining questions. Let me see from the others. Are they similar to what you've just done? Okay, 33, 35, and 37 are all actually kind of similar. Okay, page 33, 35, and 37 are all very similar to the questions that I've just discussed with you. So probably this one you can actually do as your homework.